Welcome friends to this second lecture of our module 2, and in this module we are basically talking about the inorganic soil components. And so in the last lecture we have started the discussion about the primary and secondary minerals, and then we briefly discussed the difference between the primary and secondary minerals. From there we have started about the Pauling's rules, and we have discussed a couple of Pauling's rules. We have started with the Pauling rule 1, and we have discussed what is coordination number, and then we have learned about the implication of coordination number, and how this coordination number basically governs how many the cations or anions will be coexisting. So in this lecture we'll start the discussion from where we finished in the last lecture, but to give you a context, let us go back and discuss couple of things from the last lecture so that the things will be more clear. So if we go back to our last couple of slides which we discussed in our which we have discussed in our last lectures. So if we go back a couple of slides back where what we have discussed in our last lecture, we started with the coordination number. Remember that there are when there is single layer of atoms of equal size, there are two types of voids. One is void V and another is void C. So obviously the void B has the triangular shape where the triangles are pointing up, and those with the triangles pointing down are known as the C voids. So as you can see here, these are basically B voids, and this is the C voids. So if you see that there are two types of arrangement, one is called the hexagonal closest packing, another is cubist closest packing. Now if we add the next layer of atoms, so let us see that if there is a single layer of atom called A, and then we are putting another next layer of atoms so that they occupy the space above the V voids, and then we are adding a next layer above the A atoms. So there will be repeating layer called the AB, just like this. And this type of packing is known as the HCP or hexagonal closest packing. It results in a hexagonal lattice with the C axis oriented perpendicular to the AB layers. And what is the cubist closest packing? Now cubic closest packing, if when we start with the A layer of atoms and then we stack a B layers of atom and just above the B voids, and there is further another layer of atom which is which is stacked over the C voids of the A layer, then there is a repeating layer structure like ABC, etc. So this layering structure is known as the cubist closest packing. Now also this cubist closest packing or CCP results in a cubic or isometric lattice with the C axis perpendicular to the layer. So isometric view means basically 3-dimensional view. As you can see from this picture, there is a 3-dimensional view where 3 layers of atom are stacked over each other, creating this packing. So we have learned about the hexagonal closest packing and cubic closest packing. So the next, this slide basically shows these two different types of packing. One is the hexagonal closed packed, another is ABFS, centered cubic. So from there we have an idea about how these layers are stacked over each other. Now another important thing which we have discussed in our last lecture is called the radius ratio. Remember, radius ratio is the relative sizes are basically it is basically the ratio of the radius between the cation and the surrounding anions. So the radius ratio is defined by this Rx and Rz, and this Rx is basically the radius of the Rx is basically the radius of the cations, whereas the Rz is the radius of the surrounding anion. So, since the anions are usually the larger than they are the larger ions, this results in decreasing values of Rx by Rz as the size of the cation decreases. So, this is called the radius ratio. So, let us go ahead and see what is the cubic coordination. So, if we decrease the size of the cations in such an arrangement, we are still allowing for the surrounding anions to touch each other and touch the cation. With decreasing size of the cations, the coordination will first results in 8 surrounding cation. As you can see in this picture, it is quite clear that this anion is basically surrounded by this 8 this cation is basically surrounded by these 8 anions, and this is called a 8-fold coordination or cubic coordination. Now, why it is called cubic coordination or 8-fold coordination? Because the shape of the objects, as you can see, the shape of the object constructed by drawing line through the centers of the larger ion is basically cube. So, the larger ions these anions. So, when you draw the lines through the center of these anions, we will get a cubic shape. So, that is why it is called the cubic coordination. So, what is the limiting radius ratio? We have discussed is the limiting radius ratio. So, if the size of the coordinated cation becomes smaller, it will become too small to touch the surrounding anions. Obviously, as you can see here, this is the cation which is surrounded by 4 anions which are larger in size. So, if the coordinated cation becomes so small that it will barely touch only the surrounding anions, then there is a concept called limiting radius ratio. So, that will occur when this Rx by Rz become too small. Now, obviously, the radius ratio of the limiting condition often called the no rattle limit, because if the radius ratio becomes smaller than that low rattle limit, then what will happen? The cation will be rattle in its side. So, it will be disrupted, the structure will be disrupted. So, let us see how we can calculate this limiting radius ratio. So, if you see this picture, it will be clear that these are the 4 cations with the radius of Rz. So, the distance between these two horizontal lines is basically 2 Rz, which is basically the combination of their radius, and if we consider the Rx as the radius of the cation, obviously the total distance from here to will be basically 2 Rx. So, obviously, based on the Pythagoras theory, we can see that the 2 Rz plus 2 Rx. So, basically 2 Rz plus 2 Rx will be its square will be basically the square of these 2 Rz square. So, based on the Pythagorean theorem, this distance, the square of this distance will be basically equal to the summation of the square of these two terms. So, as you can see, 2 Rz plus 2 Rx, which is the total distance, is basically the summation of these two terms, square of these terms. So, if we simplify that, we will get this Rx by Rz value of 0.732. So, this Rx by Rz value of less than 0.732, the cation will be, if this Rx by Rz, that means if the radius ratio goes below this value of 0.732, then it will be too small that it will rattle in its sides, and the structure will no longer will be stable, and then it will be changing to the 6-fold coordination. So, this is the implication of this no rattle limit. So, this is the 6-fold coordination, as you can see. Now, this is also known as the octahedral coordination, because this shape which is defined by drawing planes through the center of the larger ions is basically showing a octahedron. So, that is all, it is called the octahedral coordination. Now, octahedral coordination is stable when the radius ratio is 0.732. However, by decreasing the radius of the cation further, that is Rx, if we go on reducing the value of Rx, we will eventually reach a limit where again the structure will rattle, the ion will rattle in its sides. So, then the coordination will change from octahedral coordination to further new coordination. So, let us see how it happens. So, if we consider the no rattle limit for 6-pole coordination, we will get the similar type of calculation. So, the no rattle limit can be basically determined by looking at the horizontal planes running through the ions labeled as C and D. So, these are the two ions labeled as C and D, and based on the again the Pythagorean theorem, we can see that this difference, that is 2 Rz plus Rx, this line is basically the square of this line is equal to the 2 Rz square plus 2 are both basically both of them are same. So, 2 Rz, and here also the difference or the summation of the radius of the cations of the anions are 2 Rz. So, Rz plus Rz 2 Rz. So, basically it will be getting 2 multiplied by 4 Rz square. So, if we simplify this equation, we will get a value of the radius ratio of 0.414. So, that also shows the no rattle limit for 6-pole coordination. So, if the radius ratio goes below the 0.414, the structure goes into 4-pole coordination. So, earlier it was 6-pole coordination, now due to the reduction of the cation size, the radius ratio changes, radius ratio reduces, and ultimately this 6-pole coordination will be converted to the 4-pole coordination. And why we call it as 4-pole coordination? Because planes through the center of the larger atoms of in this case will form a tetrahedron like structure. So, that is called a 4-pole coordination, also known as the tetrahedral coordination. So, let us see one example. So, you can see here this is a tetrahedral coordination, and in this tetrahedral coordination obviously at the center there will be a the cation which is surrounded by 4 anions. So, what is the no rattle limit for 4-fold coordination? So, the no rattle limit of tetrahedral coordination is reached when the radius ratio becomes 0.225. So, if the radius ratio goes below 0.225, then this 4-fold coordination will no longer be valid, or there will be rattling of the cations, and as a result of that this 4-fold coordination will converted into 3-fold coordination, and so all known as the or it is known as the triangular coordination. So, for triangular coordination you have to remember that the coordination number is 3, that is 3 ions are surrounded by 3 ions are surrounded the smaller cation. So, as you can see here, this is a 3-fold coordination or triangular coordination, where the small cation is basically surrounded by 3 anions, larger anions. Obviously, as you can see visually, one difference that as we are going from 8-fold coordination to 6-fold coordination to 4-fold coordination to 3-fold coordination, you are seeing that the size of the cation is going continuously down. So, a no rattle limit for this 3 or triangular coordination also will appear at a value of 0.155. So, if we calculate the no rattle limit for this triangular coordination, we will get a value of 0.155. So, if the radius ratio goes below 0.155, then the only way the smaller ion can be coordinated if we get a linear kind of combination. What do you mean by linear kind of combination? That means the 2 of the larger anions will be the 2 sides of the cation. So, this is called the 2-fold coordination, also known as the linear coordination. So, as you can see from the 8-fold coordination to 6-fold coordination to 4-fold coordination to 3-fold coordination to 2-fold coordination, we are continuously changing based on the reducing radius ratio, or in other terms by reducing the size of the cations. As the reducing the size of the cations, we wanted to make sure that the cations are barely touching the surrounding anions, and that is why we have calculated this no rattling limit. And if the radius ratio goes below the no rattling limit, then it will rattle and then it will be converting to a new coordination number. So, based on the Pauling rule 1, there are certain limits and the values of the radius ratio and also the corresponding coordination number and type of this coordination coordination structure are given in this table. As you can see that when the radius ratio is 1, obviously we are getting a coordination number of 12 and basically we are getting the hexagonal or cubic closest packing. And when it is from 1 to 7.732, we are getting a cubic packing, and from 0.73 to 0.414 we are getting a 6-fold coordination. The shape is octahedral. From 0.414 to 0.225 the coordination number is 4 and we are getting a tetrahedral combination, tetrahedral shape, and then from 0.225 to 0.155 we are getting coordination number of 3 and we are getting a triangular arrangement of the ions, and finally when the radius ratio goes below 0.155 then we are getting the 2-fold coordination, that and the arrangement will be kind of linear. So, all these different types of packings are presented here. As you can see that in case of coordination number 3 where we are seeing it will be basically a triangular as I have mentioned, and also in case of coordination number 4 we are seeing a tetrahedral shape. When the coordination number is 6 we are getting a octahedral shape, and for coordination number 8 we are getting an corners of a cube, that means a cubical shape here, and finally for the for the coordination number 12, that is a hexagonal or cubic closest packing, we are getting a basically corners of octahedron. So, for example, if the ionic radii for oxygen anion is basically 0.14 nanometer, and also the ionic radii for silica cation is 0.039 nanometer. So, obviously, if we consider the silicon and oxygen and calculate the radius ratio, we will be getting a value of 0.279. So, this 0.279 basically comes in this range, that is tetrahedral combination or tetrahedral structure where the coordination number is 4. So, basically 4 oxygen anion can surround the silica cation and results in a tetrahedral coordination. So, this is basically the implication of Pauling rule 1. Also, we can see here different ions, cations and anions and their ionic radii and also their radius ratio and corresponding coordination number. So, one thing is clear that aluminum which is 3 plus aluminum cation can exist in either tetrahedral or octahedral coordination with oxygen anion depending on its temperature of crystallization, because if the higher the temperature, lower the coordination number. It is a thumb rule. So, if there is a higher temperature, then there will be lower coordination number. So, from this Pauling's rule we can basically identify for each of these cation what will be their coordination number. Now, let us move to the Pauling's rule 2. So, Pauling's rule 2 says that, also known as the electrostatic valency principle. So, it states that in a stable coordination structure, the total strength of the valency bonds which reach an anion from all neighboring cations is equal to the charge of the anion. So, basically the strength of the anion bond is expressed as this small s, which is basically calculated by a ratio of Z to Cn, where S is the electrostatic bond strength to each coordinated anion, Z is the valency of the cation, and Cn, as you know, that is the coordination number. So, in effect the charge on a cation is shared equally among the nearest neighboring atom, which is basically very clear from this formula, because the strength of a particular bond can be calculated by dividing the valency of a particular cation by the coordination number, that means number of surrounding anions. So, if we divide the valency of a particular cation by the number of surrounding anions, obviously the charge of that cation will be shared equally among the nearest neighbor anions. Now, for example, for silica, that in the tetrahedral coordination, the SI bond strength is basically 4 by 4, that is 1. In case of aluminum, substitution for silica, which will discuss very soon, while we will discuss the isomorphous substitution, you will see that aluminum sometimes substitutes the silica in the tetrahedral coordination. So, in that case, the aluminum oxygen bond strength become 3/4, where 3 is basically the valency of the cation, that is aluminum, and the coordination number is basically 4. So, we are getting 0.75. So, bond strength is decreasing when you are moving from silica tetrahedra to a tetrahedra where a silica is substituted by aluminum. So, for aluminum in octahedral coordination, aluminum oxygen bond strength becomes 3/6, where 3 is basically the valency of aluminum and oxygen coordination number is 6. So, we are getting 0.5. So, the electrostatic attraction of the cation to one anion is reduced if another anion is attracting the cation in another direction. So, if we see the Pauling's rule 3, the rule 3 states the existence of edges and particularly of faces common to the anion polyhedra in a coordinated structure decreases its stability. So, as these different coordinated different coordinated polyhedras are sharing their edges, their faces, we get a notion that obviously when they are joining together by sharing their faces, obviously their stability will be decreasing. So, this effect is large for cations with high valency and small coordination number. Why it is that? Because the closer the cation, there is unstable the coordination. Obviously, when the closer when the cations become closer, obviously there will be electrostatic repulsion. As a result of that, there will be basically instability in the structure. So, especially this type of instability is large when the radius ratio approaches the lower limit of the stability of the polyhedron. So, obviously, when the radius ratio is going down, that means the size of the cation is going down, and subsequently the valency of the cation is increasing and small coordination number we are getting. Obviously, there will be chance for destabilizing the structure. So, this is basically the essence of Pauling's rule 3. So, if you can see here in this picture, obviously you can see this is a single tetrahedral unit where the silica is surrounded by 4 oxygen cations, and these sheets of tetrahedra basically will form by sharing their, there are 3 ways they can bond together. One is by point to point, which is the most stable, another is edge to edge, and third is the face to face. As you can see in this, the sheets of tetrahedra are basically linked together by point to point bonding. So, in case of octahedral unit, in case of aluminum, let us consider an aluminum octahedral unit where the central atom cation is the aluminum, which is surrounded by 6 hydroxyl ions, giving a octahedral shape. These octahedral shape basically they share their edges. These octahedral share their edges to form a sheets of octahedra, which we will see very soon. So, basically with cations of higher valence like silica, tetrahedral has point to point bonding, and with aluminum there is an edge to edge bonding. Okay. So, obviously, when there is an edge to edge bonding, it will be less stable than that of point to point bonding. So, you can see there are different types of structure and how they share, how they link between each other. You can see that tetrahedral, this is a single tetrahedral unit and they are sharing their corners, and here you can see there when they are sharing their edges. This is octahedral unit when they are sharing their corners, and this is the sharing their edges. And this is a cubic coordination, and this is basically sharing their corner and sharing their edges. Remember that when they are sharing their edges, the chance of destabilization is much more than that of sharing their corners. Now, Pauling's rule 4. The Pauling's rule 4 states in a crystal containing different cations, those of high valency and small coordination number will basically tend not to share polyhedron elements with each other. So, basically this is because the electrostatic bond strength for bonds between this cation and this coordinated anions will be relatively large. So, obviously that says that higher the valency cation, higher valency cation tends to stay as far apart from others as possible. Now, remember that if the bond strength is more than half of the charge of the anion, it is unlikely that the anion will have more than one bond to the same cation with the same coordination number. So, this is our Pauling's rule 4. Now, let us see the last rule which we will discuss today, that is Pauling's rule 5. Pauling's rule 5 says the number of essentially different kinds of constituents in a crystal tends to be small. So, obviously the constituents here, by mentioning different constituents, basically meaning the configurations like tetrahedra and octahedra. Obviously the complex the structure, the higher the potential energy, higher its potential energy and hence instability. Because the substance always tend to be in a state of lowest possible potential energy. So, more complex the structure of the crystallographic structure, there is more chance of instability. So, this is this is the rule 5. So, guys, we have already covered different types of all 5 rules of Pauling's, and why we have discussed this Pauling's rule will be more clear when we discuss the structure of clay minerals. So, before describing the structure of the clay minerals, it is important that we discuss the soil silicates. There are different types of structure which you can see if we classify the soil silicates. First of all, called the nesosilicates, and nesosilicates is basically built by the single separate silica tetrahedra. One example, as you can see, it is olivine. What is the next comes the sorosilicates. Now, the sorosilicates is the structure where 2 or more linked tetrahedra and giving the formula of either Si2O7 or Si5O16. And the example of sorosilicates is here given, that is epidote. Now, inosilicate is basically defined by single or double chain of tetrahedra with the basic structural unit of formula of SiO3 or Si4O11. Also, you can see the example of basically the example of inosilicate here calls the pyroxenes. So, this is basically single or inosilicates, again it is basically showing the single or double chains of tetrahedra. Now, next is the cyclosilicates. Cyclosilicates are basically the closed ring or double rings of tetrahedra, as you can see, example is benitoline. And phyllosilicates, this is the most important thing as far as the soil is concerned, because this is the building block of the clay mineral, which is the most reactive, one of the most reactive fractions of soils. So, as you can see that phyllosilicates is basically sheets of tetrahedra with the basic formula of Si2O5 producing a phylum, that means a leaf like structure, that is why it is called the phyllosilicates. And finally, the final one is called the tectosilicates, which is basically a stable framework of tetrahedra producing a formula of SiO2. And the example of this tectosilicate is basically feldspar, quartz and the other primary minerals. So, guys, you have seen that we have discussed today in details about the 5 Pauling's rule, and also we have discussed the basic classification of the soil silicates. In the next lecture, we will start from the structure of individual clay minerals, and then we will discuss their individual properties based on their structure. Thank you, and let us join in our next lecture.